Okie doke. All right, how we all doing tonight? You guys can hear me okay? All right, cool. Um, let's see. So where we are is we are now in the last 2 weeks of the semester of the summer. So where we're at is today. The web homework's due. So I guess the first thing I'll say is, do you guys have any questions on the web page stuff or the web page homework? Or are you having any trouble getting the web page stuff to work? Anything like that? This would be a good time for me to answer any questions you have about web stuff if you have any questions about it. Hopefully you guys have all gotten through the lab. I know a lot of people haven't sent me the lab, so send it. I guess in passing, I'll say that I've now sent back the first two homeworks. The binary number homework was homework 1, and the machine language homework was homework 2. I've usually write back one way or the other from the labs that you sent. So if you have not gotten feedback from me on the labs and the homeworks, and you think you have sent me labs or homeworks, make sure to let me know, because that means that I have not graded your homeworks and you're not getting credit for them. So yeah, do them. All right. So the web homeworks due today. To this week, we're gonna do writing programs in a language called Scratch, which I'll explain to you guys in a little bit here. Next week, we'll talk about how to design and analyze algorithms, ways to think about algorithms as a computer science thing, ways to design solutions to problems, way to talk about whether my algorithm is better than your algorithm, that sort of stuff. So as far as, let's do it this way. The things remaining for you to do this semester, today's homework 3, this week is lab 4 and homework 4. They're both up on Blackboard already. Next week, lab 5 and homework 5, and then that's the last week of the summer. Also next week, I'm going to hand out the take-home final, which is meant to be questions on kind of all of the big topics we've done all semester. I need to ask the people in the registrar's office what the last day I can submit grades for this course is. And then based on what they tell me, I will set the date of when all of the final and stuff like that is due. Basically, I'm going to try to make it be as late as I possibly can still giving me a day or so to grade everything before the deadline. So whatever the deadline is for handing in the final grades, take off a day, and I'll be like the day everything has to get to me so I can grade it. Okay. Um, so that's the plan. So you can look at this and see it's a lot of stuff. I think it is kind of a lot of stuff. It is still, the vast majority of your grade for the years is still listed right here, right? So if you fell behind in the first couple of homeworks or you're feeling lost, there's still plenty of time and plenty of points left to make it up. So don't be discouraged. On the other hand, it's a lot. It's 2 more weeks of the semester, and we're going to do 2 more weeks of new stuff. Okay. So any questions on the plan, on the schedule, anything like that? Make sense? Yeah, I'll send you out something. Whether it's a study guide, if I have it, I will try to send out like a practice test. That's what I usually do. So you can have practice questions of the same kind of thing as what the final is. But again, since the final is take home, you will see the questions and be able to use those to look up from our old lectures and homeworks and stuff like that, the stuff you need to do. So I'm not, it's not like you need to have a list of things you need to memorize for a final because it's take home. It'll be open book, open. Basically, it'll be open stuff from this class, closed people in this class, and closed, copying stuff from the internet. But anything in the book, anything in any of the lectures, anything in any of the labs, anything in any of the homeworks, anything in any of the recordings, all that's fair game. So I can make stuff like that for you if you want, but I guess it's not the same kind of thing you need to study for, if that makes sense. So yeah. Any other questions on the plan or anything? All right. So like I said, this week is about programs and programming languages. So the first day of class and all along I've been saying computer science is the study of algorithms where an algorithm is a step-by-step solution to a problem. What I want to focus on this week is we also talked about programs on the first day. A program is an algorithm where the steps are written in a language a computer can understand. So, in week 2, we talked about machine language. And maybe that's still giving you nightmares, I don't know. But the point is that the reason I inflicted that on you is partially to get you to understand the difference between an algorithm and a program, and what algorithms get you and what computers can actually do, and to get a feel for the level at which computers actually do their work in. In machine language, every instruction in machine language is implemented as electronic circuits. So, for example, one of the instructions we had was add, which means somebody wrote, well, every computer in it has a circuit that takes a bunch of wires that have bits on them that is interpreted as a number, and then another set of wires that is the other thing you're adding. 0 means off, 1 means on, 0, for bits, and then spits out as wires in a circuit the sum. How does that work? I don't want to get into it, but it's done as electronic circuits, as wires with power on them and not. And basically, as far as the computer is concerned, all they're doing is taking wires that have power or not, doing some kind of electronic circuitry manipulation to it, and generating power or not on other wires. Okay? So the reason why all of the machine language stuff we did 2 weeks ago, the instructions were so low level or basic or simple, was because every instruction that you see has to be implemented as circuits. And so circuits can do some things, but they can't do lots of complicated things. Instead, what we do is we combine lots of simple things over and over again and make complicated things. So the other thing is, basically, no real programming is done in machine language. When people are doing programming and they're programming web pages, or they're programming databases, or they're programming game, AI devices that can chat with you or whatever, they're not writing those things in machine language because, as you've seen, writing things in machine language sucks, right? Getting all of the numbers right and getting the order right and having to write 10 lines for something very simple and all that is tedious, even for people who like programming, okay? So instead, machine language is tedious. IOUS. Instead, people have developed what are called high-level languages. These languages have instructions that, I'll say, look closer to English. And so instead of being a weird mishmash of binary or hexadecimal numbers, there's words like if or forever or things like that. Programs that are written in high-level languages get translated into the machine language of the computer you're using. So how does that work? Again, I don't want to get into it, but since the only thing a computer understands is machine language instructions, things that can be implemented as circuits, then somebody has to take these high-level language statements, things that look like English, and turn them into an equivalent set of things written in machine language. Okay, so that's what happens behind the scenes when you're doing something in a high-level language. And you're going to be doing some work in a high-level language here in a minute. So that's what's happening when you do this. Okay. I can't spell. Lots of high-level languages exist. If you ever heard people talking about stuff, the one we use here is C++. Other places use Java, or there's a language called, Python. There's a million, like literally hundreds and thousands of others. Um, um, all these languages, including the one you're going to use, all have certain things in common. Okay, they have ways to turn common groups of machine instructions into a single high-level instruction. And then once you do that, you can forget that all of the low-level stuff exists. So an example of this is, for example, subtraction. If you remember the machine language lab and homework, in that lab and homework, subtracting was a big pain in the ass, right? You had to take a register, set it up with the FF, do the instruction 9. That flips the bits. You have to take another register, put a 1 in it. You have to add the 1 to the flip thing, and that makes the number negative. Then you have to take the number that you made negative, you have to add it to the original number, and that finally subtracts it. That's a whole lot of stuff for just minus, right? High-level languages say, why don't I let you do minus as an operation? And when I do the translation into machine language, when you want to run your high-level language program, I will automatically generate the correct machine language instructions to do that for you. Okay, and then as a user of the high-level language, you can forget that this translation happens. The high-level language says, here, have a subtract instruction. You say, nifty, I know what it means to subtract. I'm going to put a subtraction instruction into my program. And then you don't have to worry about what machine language instructions are replacing that subtract when you actually implement it. You don't have to worry about how the subtract works. You just trust that it all works correctly and it all comes out fine. So the word for this, the term for having a high-level structure, here the structure is an instruction, do a task that would normally require a lot of details is called abstraction. Abstraction means we're going to hide the details of how something works and show you a common way of doing things that doesn't really exist. Okay? So an abstraction is a way of doing things that doesn't really exist because really it's more detailed than that. But you can use it like it does exist. So examples of this. So I'm talking about programming language instructions. I can't spell. Programming language instructions. Well, high level. Programming language instructions. A lot of them don't really exist because they get turned into machine language instructions. Things like printing a document. You just press the print button, but lots of things go on behind the scenes, sending signals to the printer and wires and electronic things on the network and stuff like that. Even stuff like, I just get back to my kids' Little League game, so I'm thinking about throwing and catching a ball, right? Once you learn how to throw and catch a ball, you don't, or ride a bike, if you want another example. You don't have to think about how it works anymore. You can say, throw it to me. And you don't say, well, to throw, what you have to do is take the ball, put it in your hand, grab the hand, take your arm, pull it back behind your head, step forward, and move your arm forward past your head fast, and let go of the ball right when it gets past your ear or something like that. You just know what it means to throw as an abstraction of all the actual things that are actually happening in your body's machine language, which is the language of muscles and moving things around and stuff like that. We know. We have abstractions for throw a ball, for cook me a hamburger, for all kinds of stuff like that. We live in a world of abstractions where we don't want to worry about the details all the time. So this comes naturally from real life, and you see it all the time in computing and stuff like that. So I just want to, we have a word for it, but this is something you've been doing all over, okay? So other kinds of abstractions in a high-level programming language. Instructions to repeat parts of the program again. So remember that in the lab, the machine language instructions to go back and do the adding over and over again. High-level languages will give you that as an abstraction. Say I want to do this 10 times, and you wrap it around 10 times. Instructions to do certain things sometimes. Instructions to label certain places in memory with human-friendly names. So you can say, give me this spot in memory, and when I'm talking about that spot in memory from now on, I'm talking about the position of something, or the A side of the triangle, or my salary, or something like that. These locations are called variables. So anyway, what these all have in common first of all, they don't really exist in machine language. Again, one of the points of inflicting the machine language homework on you was to make you understand just what a computer does under the hood. And when we write these more powerful instructions that are going to change colors of things on the screen and things like that, know that that these are really abstractions of low-level basic machine language instructions written in binary that have that the translation's automatically happening for you. And you don't have to worry about that because you can pretend that they do. You don't have to worry about what the computer's actually doing. You have to worry about what kinds of instructions the high-level language you've chosen provides to you as abstractions of the real thing, and use those abstractions as if they really were existing on the computer. And we'll even use words like, this instruction makes the computer do this, when I guess technically what we should be saying is, this instruction, when translated into machine language, generates a series of machine instructions that make the computer do this. Okay, but we never say that. A, it's too much work, and B, when we think about the abstraction, we think about it as a thing that actually can happen. That's the point of the abstraction. Okay, so this is all a big prelude to say the high-level language we are going to use in this class is called Scratch. It's free. You need to sign up for an account at scratch.mit.edu. The language provides a lot of abstractions to let you quickly and easily do graphical stuff. Things on the screen moving around, that kind of thing. So what I'm going to do now is I'm going to load up the web browser so you can see how this works. This is my awesome unicorn webpage from last time. And then I'm going to go to scratch.mit.edu. I already have an account. So assuming this loads, I will sign in. And what you get, click the create. And when you get a new Scratch program, a new Scratch project, we wait for it to load. And what you ought to see right now is a screen with this disturbing looking cat thing on it. You guys all see that? It's coming up for you? Okay. This is the world in which action is going to happen. You can, I think, make things bigger. Grow that? No. I thought there was a way to, I can shrink the cat. There's a way to make this window bigger. Oh, that's it. This little blue rectangle thing in the upper left makes the whole thing bigger. But I want to leave it like this because over here in the big empty gray void on the right here, that's where the program's going to go. So in Scratch, programs are called scripts, and scripts start with events. So if you, up here, I don't know if you can see them. I can't make the font bigger, I don't think. Let's see what happens if I, no. Do I have a, yeah, I don't think so. Not what I want to go away. So yeah, I don't think I can make this make the words any bigger. But what you see on the top of the middle is a bunch of colored buttons with words next to them: motion, look, sound, pen, data, events, control, sensing, blah, blah, blah. Everything starts with events. So if I click on the events, I get a list of things that happen. Generally speaking, I want things to start when the green flag is clicked. That's this green flag here on top of the white page. And so what you can then do is add extra steps, and all of these steps click on to the previous other steps like puzzle pieces, and you know they're going to click together if you get this white line. Hopefully you can see the white line underneath the place it's going to go. You let go and it goes zoop in there. Okay, and then oh, I don't know. Let's try this. This is stupid. So this says, when the flag is clicked, say hello for 2 seconds, and then turn clockwise 15 degrees. And so if I click the flag, he says hello for 2 seconds, and then he turns. And I click it again, he says hello for 2 more seconds, and then he turns. And 2 seconds is too long for me, so I'm going to change this 2 seconds to 0.5 seconds, and I'm going to change this 15 degrees to something more like 45 degrees. And so you can, anything in a white box like this is something you can change around. And so you can click the flag, and he says hello, 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 hello. And so you can keep clicking the flag and make him move around over and over and over again. Okay. What he's doing is when the flag is clicked, things here happen in this order. Okay. So what you're seeing is a program, a really simple and not very exciting program, but a program that moves the cat and makes him say something when the flag is clicked. So what we can do is we can take that program and we can make it more interesting. We can add more stuff to it. We can do a different program. We can make it talk to other things on the screen, and so on. So the lab walks you through some things you can do to this these scripts. I want to give you a couple of more examples of things just so you can see what we're talking about here. One thing we can do in the control tab is control how the cat moves around. So what I can do, for example, is detach these puzzle pieces down here for a second. Say repeat 10, and then do this. Now you see how the repeat kind of can wrap around any number of instructions, and this could get bigger or smaller based on how many things are in here. I could put 100 instructions, and the repeat will just grow to cover all of them. So when I attach this, because whoops. Well, so what I do is I change the order. Let's put it back to the order I started with. If I attach this, now it says when the green flag is clicked 10 times, say hello and turn. So if I click the flag, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hellos, 10 turns after each hello. Okay, because I say hello and turn 10 times. And then you could put stuff after the repeat if you wanted to. I don't know if this is going to work too well. Play sound meow. Let's see what this does. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Dang, that was loud. You guys hear that meow? Because holy crap. So the reason why you heard the meow after 10 moves was because I repeated moving 10 times and played the meow at the end. If I put the meow in here, now the repeat wraps around the play sound instruction as well. And so this is going to be 10 hellos, 10 turns, 10 meows. You guys awake yet? Okay, so the point is, again, well, one of the points is these are all abstractions of actual machine instructions that do things in binary numbers and hexadecimal and all that stuff. I don't know how any of that works, and this is all getting turned into that for you. But second of all, when you're thinking about this, you want to think about how you want the cat to do various things, And so you want to think about what your plan is. There's repeat. There's one of the things that you see a lot of in the lab is forever. Forever means do the stuff that I'm wrapping around forever. And notice there's not even a way to attach other pieces here. I can't take a new instruction and throw it after the forever. It doesn't attach because it's not like I can do anything after the forever. The forever goes on forever, right? Until I click this, I'm not going to let it go forever. Clicking the stop sign stops it. So just so you know. What other sounds do I have? I can record something. So the other thing I can do, I'm going to get rid of the sound because that's annoying. I can do things like if then. If then is a way of seeing if something is true or not. So one thing I could do is forever say hello and, well, I'll do this way. This says, well, I'll start it this way. This says forever say hello and turn, right? This says what I could do is, you're going to have to trust me on this, but there's a sensing that says, ooh, touching mouse pointer, let's do that. If you're touched, so this says is if the cat is touching the mouse pointer, whoa, then what should we do if it touches the mouse pointer? Then I'm trying to think of something interesting that can happen. Move 10 steps. That'll move it forward. So now it's that. Oops. Why is this not doing anything? That's weird. Stop. Wonder why it's not turning anymore. What did I do? I somehow broke it. This is exciting. Somehow it got trapped in some kind of weird rotation. But there it is. All right. So this is the cat from before. This is the program I had before. 15 degrees and turning. I'm gonna. Okay. And then I'm gonna stop the script, and then I'm gonna add the touching mouse pointer thing. This is what I was trying to do before. Hello, 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 hello. If it touches me, it moves. Boop, boop. See, it's boop, 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 boop. And so it kind of moves around the screen. Not much, and it depends on which way it's pointing. So it moves kind of in the direction it's pointing, and then it'll spin in place when I take the mouse off of it. Bloop, 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 bloop. Another thing I could do, here's another fun one. If touching the mouse pointer, how do I change my size? I think it's in looks. Change size by 10. Let's see what this does. So I click the flag, it says hello and turns. When it touches the mouse, it gets bigger because it's changed size by 10 means its size gets bigger by 10. Some of these numbers are kind of arbitrary. And so blah, blah, blah. Probably it's a good idea, and then I'll keep spinning after that. Probably it's a good idea to, so what I would like to do now is I'd like to make it when the flag starts over, I have this stupid big cat now, right? I want to reset it. So one thing I can do is I could set my size to 100%, which is your regular size, right when I click the flag. So when I click the flag now, the first thing that happens is the size to 100%. The rotation style gets set to the correct rotation style, which I don't know how it got changed. And then it turns and says hello until text now. So boop, back to small. Hello, 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 turn, 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 turn. Hello, 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 turn, 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 turn. Bloop. And then I put the mouse on it, and it'll slowly get bigger and bigger and bigger and bigger and bigger and inflate and inflate and inflate forever. All right, so again, the lab is going to take you through this kind of step by step. I want to show you some things about how it works, because I won't be there to watch you in the lab. Do you have any questions about this program, at least, or what it's trying to do or how it works? Why I'd want to do something like this is a separate question. I don't know. But the homework this week is to make something cool in Scratch. And so by the end of the lab, you should be able to, have ideas about stuff like that. And so I did this in my spring semester class, and people came up with some really cool stuff. Somebody did like an air hockey simulator. Somebody did a really complicated game. So there's a lot of things you can do with this. You can make sprites appear and disappear. You can make sprites talk to each other. You can make sounds pop up. All kinds of things like that. All right, so far so good. This makes sense. You kind of see what the program does and how what's going on the script maps what's going on the screen. That sounds right. Okay. I want to do a couple of other things while I'm here that's hard to explain in the lab. First is you're allowed to edit the way sprites look. Okay, so there's more of these sprite pictures in here. You go to new sprite and there's a couple of choices here. Choose sprite from library pops up. Can you see the thing that popped up, or is this a pop-up menu you're not going to get? Can you guys see the picture of all these pictures here? Okay, cool. So these are all sprites that came with the Scratch program. And you can map down, and there's all kinds of them. Some of them are stupider than others. It's kind of a mix of different animation styles, which I'm not a fan of. But you can, if you want other sprites, you can do whatever you want here and take them out and go crazy. There's balls, there's people, there's dinosaurs, there's, there used to be things that looked like buttons. I'm trying to, there it is, that you can use for buttons for things, cars, all kinds of stuff like that. So that's one way to do it. I usually pick the ball, that sort of thing. So now I have two sprites, and I have two scripts. And maybe this sprite has a script that says when the flag is clicked, forever, I don't know. Turning seems kind of stupid for a ball. Here's what I think I make you do in the lab. Move 10 steps, and if on the edge, bounce the other direction. And so now I got a spinning cat and a bouncing ball. Boing, boing. Forever move 10 steps. If it's on the edge, bounce the other way. Boing, boing, boing. All right. You can also use the paint here to either edit what's on the ball. And so I can make, I don't know, a little hat. I can draw a little hat for my ball. I am awful at drawing, so I don't usually do this. So now my ball's a little hat, see it changes on there, and when I tell it to go, it bounces back and forth. The hat goes upside down because bouncing bounces you, makes you opposite, so opposite of up is down. So you can draw your own sprites. So here's a new sprite I can draw. Again, I'm awful at drawing. You can do things like this and have like a doorway on your screen where things are bouncing in between, stuff like that. So anyway, the editing tools, I think I talk about them in here, these are all sprite editing tools, and you can change the way the sprites look. You can add stuff to sprites. You can draw your own sprites. You can add text. For all the good that does you. So now I got something that says woo, because woo. So the point here, I'm just showing you stuff you can do. Okay, that what I want you to do in the lab, I show you specific things to do in the lab, and then in the homework, again, the whole homework is make something cool. Okay, I'm intentionally being vague about what I mean by something cool. But it should kind of hold together. It should make sense. It should not be like a giant mishmash of bizarre crap like this is. Um, so use your imagination, impress me. Really cool things get extra credit. So if you want to make up for a less good first couple of homeworks, this is a good opportunity. And then when you're done, what you're going to do is you're going to hit save now. Make sure you save before you leave the page. Okay, that's the save button up here. And then give it a name. CS103 June. What's today? The 14th. Give it a title. And then if you want other people to see your sprite, you can click the share button. And what the share button does is it makes everybody able to see your script. Okay, this is important because the only way I can see the stuff you did for the lab, and the only way I can see the stuff you do for the homework is if you share it. Okay, and then you can go to your, and then up here will be your username instead of mine, and you can go to my stuff, and you get a whole list of all of the scripts that you've made over time. And then they all have different web addresses. And so the number up here is the web address. And what you would send me, like for the lab or the homework, is just the web address of the script you made. Try hard, because you're going to need to keep a bunch of these, to remember that when you're done with something, especially in the lab, when you're done with something and ready to go on and add to it, that what you want to do is you want to save a copy of the thing you were handing in before you change it. Because otherwise what's going to happen is you're going to send me the link to the thing you did for the lab, and then you're in between when you sent me that link and when I get a chance to look at that link, you're going to have changed your script and it won't do what you thought it would do anymore. Okay? Make sense? Questions on the Scratch stuff so far? Okay. Trying to think of a couple of cool. So here's a couple of cool things. I make my kids do this Scratch stuff. They don't actually do the programming. Yeah, I hope so. So my kids like it. They we'll see. There's still numbers involved, right? The turning by a certain number of degrees is still a number. So my kids make me write programs like this, and they tell me what they want the program to do, and I try to make it happen. So here's a simple program my 4-year-old made me write. This is probably too easy for a homework, but just so you can see the kind of stuff. What this script does is it's got two bats in it, and the bats will always talk to each other forever, and if they're talking to the other bat, they'll bounce to a random place on the board. And so the bats kind of bounce, they say hello, and then off they go. And so they're using this pick random, they go to random locations on the board, and they just bounce around and give you epilepsy. And this is just a 5-line script here. Again, this is too simple for what I think a homework would be. What my 7-year-old wanted me to do, and I think I might explain this to you more next time so you can see what a complicated Scratch program would look like once you've seen the basics in the lab. Where did I put the dragon one? think no, that's not it. I think it's this one. So he wanted a game with a dragon and a knight. And so what you have to do for this game is you're the dragon, okay? And when the flag is clicked, when the flag is okay, you can move the dragon around by using the arrow keys. This badly drawn green thing in the middle is a wall. If you hit the wall, you die. Okay, and then you have to start over. Stop the script. Start the script. There's a way to turn on and off your fire. Okay, if you make it through the middle and hit the knight, but you hit him without turning on your fire, he kills you. Okay. If you manage to make it through the middle and turn on your fire and burn the knight, he dies. He says, ouch. And then we go to phase 2. In phase 2, it's hard to see this because I'm pressing keys, but you're moving the dragon with the arrow keys, but he's getting I'm not touching a key right now. Okay, I can push the up arrow to make him go up, but he falls down by gravity. This is what you wanted. Okay, and if you land on these purple things, it's not perfect because this fire's kind of holding them up, but they're platforms like in a Mario game. If you hit the black, you die. Okay, so. Don't forget your fire. Phase 2. And so if I hit the black, I die. Again, if I go through here and I burn the knight again, an exit opens up, and we haven't gotten this far, but when the exit opens up, I should be able to go through the exit to get to board 3, which we haven't written yet. So this is the kind of stuff you can do. And so if you're saying to yourself, holy hell, how am I going to ever make that happen? Don't expect to understand what this script does. It'll make a lot more sense after you do some of the lab. But I just wanted to show you some of the cooler, more advanced stuff you can do that you can come up with as you're playing around with this. So try very hard to give yourself time to do the lab early so that you have a lot of time to play around with cool ideas for the homework. Okay, and then share with me. Feel free to ask me questions about what the right kind of thing you want to do for the homework is. It'd be great if we came on Thursday and had questions about stuff you were stuck on for the homework, for the lab, and how to make things happen. There's a lot of weird advanced stuff that I had to figure out. Here's another one. I don't know if I have this one. This is one somebody did for. I think it was this one. What he wanted, this was super hard. He wanted to have the cat walk around. This is what one of the students last year wanted, and drop a line behind him. And I don't know if you can see it, but the line's in 2 different colors. Because what he wants that if you touch the line again, you die. Okay? But the problem we had was the cat is automatically touching the line he dropped. And so the way we hacked it was we made the line he drops be one color, and it's followed by a line of a different color, so that, I'm kind of trapped now, so that if you hit the blue, you're okay, if you hit the purple, you die. Anyway, you shouldn't, I'm just showing off stuff now. You shouldn't need to understand how this works. I just want to kind of inspire your imagination a little bit for things you can do so that you can get an ideas for what you can do on the homework. There's lots of opportunities for cool stuff. Again, if you do something that's really above and beyond the stuff in the lab, I am totally willing and desirous to give out extra credit on this stuff. So impress the hell out of me and get extra credit. All right. Any questions on the Scratch stuff? All right. If not, start playing around with it and come on Thursday with questions, and I'll spend as much time as you want on Thursday answering questions. And I will stop the recording.